Good day to you. PTQ Magazine and Digital Refining are pleased to bring you this webinar featuring Swagelok. My name is Ken Molay. I'll be acting as your facilitator. I'll be turning things over to Matt Dixon, Application Commercialization Manager for Swagelok. Matt has worked as an assembly, welding, and manufacturing engineer at Swagelok, supporting the production of high-volume fittings and hose product lines, as well as designing and building assembly and test equipment. In 2004, Matt joined the Custom Solutions team and is now a leading integration and application expert within the Swagelok organization. Matt's experience in sampling systems includes development of the Grab Sample module and Grab Sample liquid product lines, as well as Swagelok's ammonia sampling system. Matt, take it away.
All right. Well, thanks, Ken, and thank you for the introduction, and thank you everybody for joining us this morning or this afternoon or evening, wherever you happen to be in the world. So let's, without further ado, let's go ahead and jump into the content. So let's just level set and make sure that everybody's on the same page. So let's talk a little bit about what is grab sampling and what, why do we do it? Well, basically, grab sampling is taking a sample out of your pipeline, your tank, your process, and then taking it to a remote laboratory for analysis. This is really a qualitative measurement. It's not quantitative. Quantitative would be something like pressure or temperature or flow. This is qualitative. It's really all about analyzing what it is that's flowing through that and the characteristics of whatever it is that's flowing through your system. Now, at Swagelok, we tend to break them down into two very broad categories. Either bottle style panels or cylinder style panels. And in industry, these are often known by a lot of different names: field sampler, lab sampler, spot sampler, or just very commonly sampler. Grab sample is probably the most common, but it's also one that's the one that we use here at Swagelok as well. So why are we doing grab sampling? What is the purpose? It's really all about validating the process and making sure that whatever it is that is flowing through that pipeline meets specifications, whether it's your internal specifications or whether it's your customer specifications. Anytime there's any sort of a change of custody. So, for example, when you have goods coming into a facility or leaving a facility, chances are there's going to be some sort of a sampling operation in order to sample that incoming feedstock or to sample that outgoing product. You may not even analyze that. You might just put it on the shelf as a reference and never actually analyze it. But anytime there's that change of custody, you're probably going to have some sort of a sampling operation. Environmental regulations. I think we all know that environmental regulations only tend to go in one direction, and that's more and more strict. So as those regulations come into play, we need to evaluate our waste streams to make sure that that they meet those regulations, whether it's our discharging to the water system or going out the smokestack, whatever that may be. We need to analyze that to make sure. And then also online analyzers. With online analyzers, you really do need to periodically validate those results that those are giving you. It's online analyzers are great that they give you essentially a real-time result, but you do need to periodically validate that. So anytime you have an online analyzer, you've got a grab sample system that's typically going to be associated with that. Now, when we're talking about sampling, there are a few basic rules that we want to adhere to. We want our sample to be timely, representative, and pure. So by representative, we want to make sure that whatever it is that we're extracting from the pipeline is a true cross section, a representation of what it is that's flowing through that pipe. So we want to do things like avoiding phase changes. Anytime you have a change of phase in your system, in your sampling system, you really have the likelihood, almost certainty, of changing the composition of your sample, and you fundamentally changed it, and very often you can't actually get it back to what it was in the past. Timeliness, we need to understand, how long does it take for us to extract that sample from the system and get it to our sample container. Now, with an online analyzer, we like to get it from the process tap to the analyzer in 1 minute or less. Now, with grab sampling, it's not that critical because there's a whole bunch of time delay in transportation and analysis in the laboratory. So it's really not that critical to get it there super quick, but we do need to understand how long it takes us. We need to understand if it's minutes or if it's hours, or in some cases, we've seen where it's actually days. So we need to evaluate the entire grab sampling system to see how long that takes. Then also purity, making sure that our system is such that it's not contaminating our sample, whether it's through a dirty container or by lack of purging, and we have old sample that's contaminating new sample, and also things like dead legs that can impact the quality of our sample. So one of the first things, of course, is that representativeness, and the way to do that starts right at the process tap. And by using a probe, it enables us to reach into the center of the pipe, and typically we're trying to reach into the middle third of the pipe because that's going to be where are going to have the most representative sample that we can extract from the pipe. If we didn't have a probe, then we would be taking that sample right from the wall of the probe, and we would have to worry about contamination potentially, lower flow along the walls of the pipe, and it's basically just not as representative. So we want to make sure that we're sampling from that middle third, in any sort of a large diameter pipe. Now, with probes, there are two basic types. We've got a fixed probe, which would be a welded style probe, which you see there on the right. And with that, you basically have a flange type connection with a piece of pipe or a tube that's welded to it. On the left, you actually see the other kind, which is a retractable probe. With a retractable probe, it enables you, as the name would imply, to withdraw that from the process. So you use a gland fitting, which you see there at the bottom left, and that would actually enable you to loosen that fitting, draw that probe back out. That would enable you to clean the pipe with, say, a pig, or maintain the probe itself. So we do have those, both styles that you'll see out there in industry. Now, that always begs the question, where do we locate that process tap? When we're locating a process tap, we want to make sure that we pick a place where we have enough pressure in order to drive the flow because we need to get the flow to our sample container. All right, so one of the most common places to do that is across a control valve. Now, with a control valve, of course, it can be open or closed by a certain amount, and that's going to cause, some sort of a differential pressure across that control valve. So we can use that differential pressure to drive the flow from the pipe to our sampler and then back into the process. So that's a really common way of doing it. Problem with a control valve, of course, is that it's variable. Just by its nature, it's going to be open a certain percentage, and that will vary by what the needs of the process are. And so as a result, our differential pressure is going to vary, which will drive our flow rates to vary. So that plays into the timeliness of our sample. So there's going to be some inconsistency there, and we may be able to live with that. That could be fine. But a better way to do it, if we have it available to us, would be to sample across a pump instead. When you're sampling across a pump, you have a nice stable differential pressure. So you would extract from you would have your sample tap on the discharge side where the pressure is higher, and then you would have a stream that goes back through the sampler and returns back to the pump inlet or the suction side of the pump. So this is really a better way to do it if you have a pump available to you. Now, if you're not returning to a process, definitely, returning to the process is better from a waste management standpoint and also from a sample purity standpoint because we can flow and get fresh sample through there. But if you're not returning to the process, you want to make sure to locate that panel as close to the process or to the pipeline as possible to minimize that length of the transport line. All right. So when we're looking at actual locations on the pipe, we need to concern ourselves with what is the orientation of the pipe and where within that pipe do we want to actually create the tap. So if we imagine we've got a piping system where we've got horizontal and vertical pipes, what's going to be the best place? Well, from when you're sampling with a liquid, sampling it from the horizontal or upward flowing pipes, those are generally going to be better. With especially the vertical upward flowing pipes, you know that those are going to be 100% full of liquid. Likewise, those pumps, those horizontal pipes at low elevations, again, those are going to be full of liquids. So you're not going to be pulling in some sort of a mixed phase when you're extracting out of your sample. Now, one of the areas you want to generally avoid is downward flowing vertical pipes. If you're sampling at a downward flowing vertical pipe, especially at higher elevations, you can have, again, that waterfall effect where you're going to have essentially a mix of gas and liquid that's going down in that pipe. And so again, you might end up pulling a mixed phase sample, which is really difficult to work with. So anytime you can, avoid doing that because you really just don't want to have to deal with a mixed phase sample. Now, if we're looking at a cross section of the pipe, where do we want to actually tap it? Do we want to tap it on the side, the top, the bottom? And you could potentially have those sample taps in any orientation, and depending on whether you're sampling a gas or a liquid, it really depends. It can really vary in terms of where you want to do it. So if we're looking at a system that has probes and you're actually reaching into the middle third of that pipeline, if you're sampling the liquid, you could probably get away with sampling from any orientation. But it is worth noting that if you sample from the bottom, then you will probably have a lot of contamination and sediment that starts to build up around the probe itself. So maybe not the best way to do it. If you can avoid sampling from the bottom, even with a probe, your sample integrity is going to be okay, but you're going to end up with that, all that contamination and sediment that builds up around the probe itself. Now, if you don't have a probe, well, definitely we want to avoid the bottom because again, we have all that contamination and that's just going to end up in our sampling system if we don't have a probe. And we also want to avoid the top because as you notice from the cross-sectional view here, you could potentially have gas at the top. And so instead of getting a liquid sample, you could actually be pulling in some vapors or potentially a mixed sample depending on the pipe itself. So we're typically going to avoid the top and the bottom and sample out of the side of the pipe if we have a horizontal pipe without a probe. All right. One of the things that also contributes to the purity of our sample and the representativeness are dead legs. These can be really detrimental to our sample. Now, a dead leg, to define it, it's really a branch in your system that doesn't have any flow. The classic example of this is a pressure gauge. Now, with a pressure gauge or a branch like that where there isn't any flow, at some point that branch fills up with liquid. We don't know how old that liquid is in there, but what we do know is that liquid, the molecules that are in that branch, are slowly diffusing in and out and contaminating our sample as the sample goes past. So let's take a look at an example. So let's say we've got a sample cylinder here, and upstream of the sample cylinder, we've got a bypass valve, as you often have upstream of a cylinder, and then you also have a pressure gauge. So notice that we do have two dead legs now. In those red areas, as I mentioned, as that flow is going past, you have the molecules that are diffusing in and out. And how old are these molecules? We really don't know, but what we do know is that they're being carried downstream into our sample cylinder, contaminating our sample. So the way to deal with those, first of all, we want to eliminate them if we can. So, for example, with that bypass valve, instead of a two-way valve on a branch, we could take a different approach and make it a three-way valve. Now it's a clean swept flow path through that valve, and there is no dead leg associated with it. And so, if we needed to bypass, we could switch that three-way valve, and there wouldn't be any sort of a dead leg that we have to worry about. Now, if we can't eliminate it, so say we have to know what the sample pressure is, how do we manage that? Well, we can manage that by actually moving the dead leg downstream of the sample cylinder. So in this case, the sample pressure upstream is more or less the same as what the sample pressure is downstream. So we can move that pressure gauge downstream, and now we've eliminated that dead leg upstream of our cylinder. Yes, you still have molecules diffusing in and out, but now they're being carried away from your sample container, not into it. So this is definitely a much better approach. Now, when we're selecting a sample, there's a lot of things that go into it. Toxicity of the sample is definitely a factor. For toxic samples, we're definitely going to want to tend towards sample cylinders. Sample cylinders are going to be have much better integrity when it comes to containing that sample. They can also maintain a sample at pressure. So if it's something that is something that's a volatile liquid or a gas that has to be maintained under pressure, then we're going to have to use a sample cylinder. However, there is an economic factor to this as well. Sample cylinder assembly, of course, is going to cost a lot more than like a glass bottle or a plastic bottle. So the economics of the situation are going to drive us to use a bottle to take a sample wherever we possibly can. So, there are a lot of different factors that play into this. One of those is what is the behavior of the sample that we're taking? How is it going to be affected by changes in temperature and pressure? Because remember, we're actually taking the sample out of the system and we're transporting it back to a remote laboratory. So in that transportation phase, there's a good chance that you could impact the temperature or even the pressure of the sample. So how is that going to react? And is it going to change phases on us? Because again, we really want to avoid any sort of a phase change that could potentially, fundamentally change our sample. So, for example, if we sampled something as a liquid that was held under pressure at a given temperature, and then we allowed that pressure to drop, how is that going to impact it? Well, we could actually cross over and go into the gaseous phase. And now maybe it's not everything, maybe it's just a few of the lighter components within our sample. So suppose, for example, that we had methane dissolved in our sample and then we allowed that pressure to drop. Now all of a sudden the methane starts to bubble out and we fundamentally change the sample. The analogy that I usually give here is it's the same as like a Coke bottle. You open up the bottle of Coke, and what happens? You drop the pressure, and all the carbon dioxide starts to bubble out of the Coke. So that's the same thing can happen with our sample. We want to avoid that phase change because it will fundamentally change our sample. So here's a diagram that probably a lot of you are familiar with. This would be the distillation tower. It's kind of the main process within a refinery. And with the distillation tower, the basic idea, of course, is that you heat or boil the crude oil, which vaporizes, and then as it goes up the distillation tower, it gets cooler and cooler, and different liquids start to condense out at different places as that temperature decreases. And anytime that you have these different hydrocarbons coming out of here, you're going to have grab sampling. The things down here at the bottom, those are going to be your heavy liquids. Those are always going to be liquids. The things up here at the top, those are your methanes, your ethanes, things like that. Those are always going to be gases. It's these things here in the middle, these volatile liquids that are kind of the interesting ones. Those are where we need to make a decision about whether we're going to use a sample cylinder or whether we're going to use a sample bottle. So here's an example, some of the hydrocarbons that might be coming out of your distillation tower. Let's look at a couple of those. So let's look first at pentane. Pentane, you can see it, look at the boiling point there. You can see it's a 36 degrees C boiling point. That's relatively low. Even here in Cleveland, Ohio, where I'm at, it does occasionally get up to 36 degrees C. We would definitely consider that to be a volatile liquid. Compare that to hexane, the one below it. We've got a temperature of 69 C. At 69 C, really no place in the world that gets up to 69 C, or at least I hope not. So that one's would be considered a non-volatile liquid. So that's about where we would draw the line. So that hexane pentane line. Anything above that, if our sample contains those hydrocarbons above that, we're going to need to maintain it under pressure in order to keep that from changing phases on us. So we'll use a sample cylinder. Anything below that, we would potentially have the option to use a bottle, assuming that the liquid wasn't toxic or other some other condition that caused us to use a sample cylinder instead. Sample cylinder assemblies, they can have a lot of variation to them, but they all look somewhat similar. You have that cylinder in the middle, typically range from little baby small 10 milliliter sample cylinders all the way up to 1 gallon cylinders. They can be single-ended, but the vast majority are double-ended, and you're actually flowing through the sample cylinder. It's most common that you would have needle valves on these cylinders. You can see ball valves on there, but you want to not really. You want to make sure that if you have a ball valve that you don't have a lever handle. because you don't want a lever handle that could potentially be bumped and opened. Because remember, we're going to be transporting this thing around. So it'd be really easy to bump a lever handle and open the valve while you're transporting it. So it would need to be some sort of an oval handle or something with a latch lock on it so that it couldn't actually open accidentally. And of course, you've got quick connects. You could potentially have bypass tubes, other various accessories, coatings, or overpressure protection, which we'll talk about in a moment. So there's a lot of different things that could go into a sample cylinder, but they're very recognizable. They all look pretty much the same. Now, when we're assembling a sample cylinder assembly, take a moment to think about this. What should the orientation of our valves be on our sample cylinder? Again, these are needle valves that have a definite flow direction. Should that flow direction be such that the arrows are pointed away from the cylinders, so that they're pointed towards the cylinder or in the direction of fill? Now, a lot of people have a knee-jerk reaction to say, well, we do it in the direction of the fill. But you need to stop and think about, what is the purpose of this needle valve? The purpose of that needle valve is actually to contain the sample in the sample cylinder. So our argument is that that needle valve should be the direction of flow should actually be away from the cylinder. And the reason for that is because a needle valve is going to be most effective at containing the pressure when the pressure is on the underside of the seat. So having those flow arrows pointed away, that means that the pressure will be on the underside of the seat. You won't have any pressure on the stem of the needle valve. As a result, it's really going to be most effective at containing that pressure and that orientation. Now, when we're filling a sample cylinder with liquid, uh, when we're doing that, we have to be really careful about filling them to be 100% liquid full. Because when you fill it to be 100% liquid full, you really stand the chance of this happening, where you could potentially have a cylinder rupture. The reason for that is because a liquid is typically going to have a higher rate of thermal expansion than the sample cylinder itself. So as the temperature rises and that liquid starts to expand, yeah, the cylinder is going to expand a little bit with it, but that liquid's going to try to expand further. And if it doesn't have a place to expand into, then that cylinder could rupture, just like what you see there on the right. So the way we deal with that, we deal with it with a few different overpressure protection options. A rupture disc and relief valve; those are the two very common ways of doing it, and also an outage tube. So let's take a quick look at a rupture disc or the relief valve. The rupture disc, which you can actually see here on the left, is just a really thin membrane that is designed to fracture at a certain pressure. So once it reaches a certain pressure, it fractures, and then the liquid would go out and squirt out the little holes there, relieving the pressure. Now, of course, that's a one-time deal. Once that's fractured, it's done, and you need to replace it. But it does save the sample cylinder, prevents it from rupturing. Likewise, with the relief valve, typically that's going to be a spring-loaded poppet, so you can use it multiple times. But the pressure would come in the bottom, push the poppet open, and then it could vent to atmosphere. Now, because both of these are venting to atmosphere, it's really not something that you can use with a toxic system fluid, because remember, somebody's carrying this thing. So if you have a release, then it's going to expose the operator. So another option would be an outage tube. Now, with an outage tube, it's designed to create a vapor space at the top of the cylinder. So as you're filling the cylinder, it creates a vapor space that is equal to, or intended to be equal to, the length of the samples of the outage tube itself. So as you fill it, once the liquid reaches the bottom of that outage tube, you have this gas, this vapor space that's trapped in the top of your cylinder. And rather than compress it, that liquid is just going to go straight out the cylinder. And now we've got a vapor space. So as they get that thermal expansion, you have some place for that liquid to expand into. So that's a good way to manage the thermal expansion of our liquid, is to provide some sort of a vapor space for it to do. Now the question is, how big is that vapor space actually going to be? But before we get there, we need to make sure that we avoid installing the outage tube upside down. So when we do that, what's going to happen, of course, is it would just act like a fountain until we get up to the top, and now our cylinder is 100% liquid full. Now, of course, that completely defeats the purpose of the outage tube. Now, we don't have that vapor space anymore, and any sort of thermal expansion is going to cause us trouble. So how do we avoid that? Well, You could do a number of things. You could avoid installing it upside down. You could add a this end up type of a graphic on the cylinder, but of course, somebody's not going to pay attention to that. A better way to do that would be to actually use different quick connects on the inlet and the outlet. So, quick connect body on the one side and a quick connect stem on the other side. That ensures that you can only install it in one orientation in the panel, and we don't have to worry about installing it upside down. Now, when we have the outage tube, the question is how much outage do we actually get? How much of a vapor space do we actually get? Again, ideally, you get the same amount of vapor space as with the length of your outage tube, but do you actually get that much? Suppose we have an example where we have 5 bar pressure coming in and 1 bar pressure coming out of our sample cylinder. These are absolute pressures. So when we do that, we end up with a vapor space that's about at that same 1 bar outlet pressure. And, as we're flowing through and filling our cylinder. But what happens then if we close our cylinder valve? Well, what's going to happen if we don't close our inlet valve is we're going to keep pushing in that liquid at 5 bar, and we're actually going to compress it until we have an equal 5 bar vapor space. But you can see now we've significantly reduced our vapor space here. So how much did we actually end up with? Well, in this case, let's take a look at an example. Let's say we had 1,000 milliliter or 1 liter cylinder with a 20% outage tube. So 200 milliliters is what our design was. And we can actually use Boyle's law to calculate what that vapor space is compressed to be based off of the change in pressure. So we have 1 bar to start with 200 milliliters, and then we compress it to 5 bar. We can solve for V2, and we can see that that is actually 40 milliliters of outage, or 4% instead of the 20% that we were targeting. So, is that enough? Maybe, maybe not. It really depends on what it is that you're sampling and the rate of thermal expansion. So, there are ways, it could be that that's not enough and that, the thermal expansion would cause us some problems and maybe cause a cylinder rupture. So there are ways we can mitigate that. So we could pre-charge the cylinder or use a back pressure regulator, for example, to increase that start pressure. So if we weren't starting at 1 bar in the vapor space, if we were starting at say 4 bar, then the proportionally that compression is much less. So we would end up with a much larger vapor space. Or of course, you could just take the easy route, which would just be to get a longer outage tube. So different ways of approaching this. Now, when we're selecting a bottle type, there are a number of different types that we can select. For high temperature and high viscosity samples that aren't toxic, we're very often going to use something like this. It's just a paint can, very commonly available, typically just made out of steel, either epoxy lined like this one is showing, or it could be plain galvanized steel. Um, I've not seen stainless steel versions of this, though they probably do exist, but very common. If you don't have a high temperature, high viscosity sample, then probably a better option would be a glass bottle. A glass bottle, of course, is impervious to just about everything except HF acid. And if you are trying to sample HF acid in a glass bottle, you're probably in trouble anyways. So definitely glass bottle is something for non-toxic samples. You can get things like a vinyl coating on there to help you from a perspective of preventing shatters if you drop it. It's still going to break, but maybe it's going to keep the big chunks of the bottle together. And if you want to, make sure that you're avoiding any sort of spilling, or you want to make sure you're containing any vapors, then you would probably add a septum cap to the top of that as well. And in that scenario, you actually fill with, you actually use needles to dispense your sample. So you would puncture that septum with 2 needles, a fill needle and a vent needle. And so as you're filling that bottle, the vent gases that are being displaced by the liquid, those go out the vent needle. So that's why you need 2 needles for that. So when you're sampling with a bottle, the best practice is to use some sort of a sampling valve apparatus. And this helps to control the flow into the bottle, either by using a needle valve or some sort of a flow restriction orifice. You've got, a shroud, which is the blue piece there to help hold the bottle. And as you're pushing it up into the needles, it helps to guide the bottle into the needles. And also it helps to protect the operator from the needles themselves, because obviously they're sharp. So we want to avoid, having the operator contact them. It could cut the operator, and it could frankly bend the needles as well. So definitely a shroud is a good practice. Another thing to remember is that bottles are not pressure containing. Yeah, sure that you could probably get a couple psi in there, but they're really intended to be operated at atmospheric pressure. So as a result, you don't want to be taking this volatile sample in a bottle, because it's really you really need to keep that under pressure in order to keep it from changing phase. So you should use a sample cylinder for that. Now, when we're looking at the needles, there are a number of different options. So if you don't have a septum and you just want to have an open top bottle, you could use that same exact sampling apparatus, but instead of having needles, you have a tube stub instead. So that would just go down into the open top of the bottle and dispense the sample. Now, if we are having needles, we need to consider the needle size. Larger needles, of course, are going to be better flow. For a more viscous sample, you're going to get better flow with that. But of course, they are going to damage the septum more, because the goal of the needle is to push through the material of the septum, just kind of push it aside, and then when you withdraw the needle, the material comes back together and reseals. So if you got a larger needle, the chances the chances of something not resealing is much higher. But a smaller needle, that will get you better life of your septum, better performance of your septum. But again, you got that flow restriction going on. Now, with regards to the point of the needle, the most common that you're going to find out there is called a lancet point, which is the one that's shown here at the top of the right. It's basically the needle cut off at a very sharp angle and then ground to a fine point here. Now, this is going to be the least expensive and the most common. But one of the downsides to that is that you've got sharp edges all the way around, and so it can sometimes do what's called coring of the septum, and I'll get to that in just a moment. Now, an alternative is a pencil point needle. With a pencil point, you're actually swaging the end of that needle closed and then grinding it to a point. And then you actually grind a side discharge hole into the side of the needle. Now, this actually eliminates the coring problem that I just talked about. So let's talk about what that coring actually is. So here we've got a bottle with a cap and a septa, and we've got two needles that are a lancet point. The ideal of what it's supposed to happen is that you push the bottle up into it, the needles pierce the septum, and then when you withdraw the bottle, you've got two slits in the septum that come back together and reseal. So the needles just push the material aside, and then it comes back together and reseals when you withdraw. But as I mentioned, you get some sharp edges all along the circumference of that needle. So what can sometimes happen is you can actually core the septum instead. And so instead of pushing the material aside, you actually cut out little slugs of material. And now when we withdraw our sample and withdraw our needle, you end up with holes in the septum. And you've got plugged needles potentially, or maybe those slugs are down in the bottom of your needle. But regardless, your septum is going to leak. You've destroyed your septum. So this is a problem. So one of the ways, again, we deal with that is to go to the pencil point. And with the pencil point, you push through, and because you only have a single sharp point and not sharp edges, there's no way that it can cut a hole in the needle. Instead, it just pierces straight through. And now when we withdraw it, we've got 2 points that have been pierced in the septum, and we don't eliminate that coring problem altogether. Now with the needle configurations, again, there's a number of different choices that we have. We've got the most common, which is going to be a side-by-side needle arrangement, where you've got two needles, again, that pierce the septum, which like we just looked at in the example. So your sample would come in through a fill needle and dispense out. And then as those gases are displaced out of the bottle, you would have the vent gases going out the vent needle. Now, in addition to that, there's a different approach to this, and that would be having concentric needles. Now, the downside to using side by side, if somebody were to push that bottle up into the needles and then accidentally rotate the bottle, well, one of two things is going to happen. It's either going to tear the septum or it's going to bend the needles, one of the two, or possibly both. So the concentric needles actually solve that problem by having a single having two needles on the same axis. And the way that's done is you have a vent needle around the outside of a fill needle. So your fill flow actually goes down through that fill needle, and then your vent flow goes in up through the annulus that is created between that space in that space between the fill needle and the vent needle. So again, now if somebody were to push a bottle up into this and then rotate it, it's just going to rotate about that one axis of those needles, and you're not going to have to worry about bending the needles or tearing the septum. I mentioned the tube stub option. With the tube stub, very similar, of course. Your flow just comes down through the tube stub and into the bottle. Some of these also do have an option for venting. So there could be a vent orifice. Again, it's not really going to be sealed to the top of the bottle because you don't have any sort of containment on the top of the bottle. But you could hook up like a venturi or vacuum pump to that vent and suck away some of those vapors while you're filling it. The last option that I'm going to show here is what's called a stinger, typically used for high temperature and high viscosity flows. So in this case, it is similar to our tube stub. We've got that same tube stub, but now we have added a steam jacket around it. So we have steam that goes around that and keeps that tube stub nice and hot. And so now when we dispense our sample, we don't have to worry about that sample cooling down and potentially plugging up. So this stinger assembly is very common for those high temperature, high viscosity samples. So this would be those things coming out of the bottom of that distillation tower. So the bitumens and things like that, where if we let them cool down, they're going to solidify or get really, really thick, and we're not going to be able to get it to flow. All right, so here at Swagelok, we've actually taken a lot of these concepts and developed them into standard sampling system designs. So we've got the grab sample module, which you see there on the left. That would be our cylinder style panel. And then, of course, we've got a line of sample cylinder assemblies that go along with it. And then finally, we've got our GSL or grab sample liquid panels here on the right. And those are designed to, take a sample out of a bottle. Now, with these, we've got a lot of different features. We've got a bunch of different flavors of these things. So we've got 8 different flavors of the GSM, the grab sample module. So that is, different flow paths, different purge options, things of that nature. We've got 7 different versions of our GSL, our bottle style configurations as well. And again, different configurations for different systems. Are they for, is it dead ended or does it return to the process? Do you want to purge or not? So these are the types of things that that we have. Got different purge options for flowing through the lines. And on the cylinder style panels, all those purge options actually purge through the quick disconnect fittings as well. Now that's important from a safety perspective if you have a toxic sample. And the reason for that is because with the toxic sample, when you disconnect the quick disconnect, you are always going to have some amount of spillage, and that can be a fraction of a milliliter. But if it's a toxic sample, you really don't want to expose the operator or the environment to that toxic sample. So purging through the quick connect is important because when you have that, when you purge through, now when you disconnect that quick connect, it's going to be the purge fluid that spills to the atmosphere and not the toxic sample. When you introduce a purge, though, some processes are tolerant of having a purge, others are not. So you need to make sure that you don't accidentally introduce that purge fluid back into the process. So with all of these panels, we made it such that the valves are aligned in such a way that you can't possibly introduce that purge gas back into the process accidentally. So, with all of these, we try to make these things as nice as possible, as easy for the operator as possible. So, minimize the number of things that the operator has to interact with. So, for example, they could, we have geared valve assemblies that minimize the number of valves they have to operate. So we also have operating instructions right there on the panel. Just make them as easy as possible. I mentioned those geared valve assemblies. So we've got either a 2 valve, like we see on the left, or a 3 valve geared assembly. So as we throw the valve here on the panel with operating with one handle, we're switching either 2 or 3 valves at the same time. So we don't have to worry about the operator having to know what sequence to operate those valves, which one goes first, what happens if they do it in the wrong orientation. All that is controlled, so we don't have to worry about that. So let's take a look at an example here. So in this case, this is our grab sample module, the cylinder style panel. And this is going to be kind of the most basic design of our grab sample module. So we've got, again, that geared valve assembly that you can see here in the schematic. We've got two valves geared together. Got our sample cylinder over here on the right. So when we first go to the sample position, we start filling up our sample cylinder, and we're flowing from the inlet to the outlet through the panel. Now we can go to the off position, and you can see our flow is shut off to the inlet. We close our sample cylinder valve, so now our sample is isolated in our sample cylinder. And then we can vent the pressure on either side, and that goes off to the vents. And now that our quick connects are depressurized, we can go ahead and disconnect them, take that cylinder off to the lab to be analyzed. Okay, well, what happens if we want to add a purge option to that? So now we've added a purge valve to this. And notice we have now a bypass tube on the cylinder assembly itself. And that's actually going to enable us to purge through those quick connects, which you see here and here. So we go to the sample position, and like before, we're filling up our sample cylinder. We've got our purge gas, but it's currently shut off. Once our sample cylinder is full, we can go to the off position. The inlet's shut off, the purge is still shut off. Isolate our sample. Go to the vent position that allows the pressure to vent out of the system. And then finally, we turn on our purge. And now our purge gas goes through all those lines, sweeps the system clean, goes through the quick disconnects, and again, uh, gets all the sample fluid out of those as well. So now when we go to disconnect our cylinder, it's going to be the purge fluid that spills to atmosphere, and not the sample fluid, which could potentially be toxic to personnel or to the environment. Of course, we can customize these panels. So, for example, if you have a low pressure sample, we could add a pump. Maybe in this case, it was a pneumatically driven pump because it was a hazardous area, and we didn't want to have to worry about electricity and class one, div two, and all the fun and expensive stuff that goes along with that. So we had a little pneumatic pump here that we put on the inlet, and that enabled us to draw the liquid sample in, pump it up, and then pump it through the sample cylinder. So this is a real nice way to customize this panel. All right, let's take a look at a different one. This is a fixed volume panel, and this would be for a bottle style panel. And one of the problems that you can sometimes have with bottle style panels is that somebody overfills the bottle and spills it on the ground. It seems like it'd be pretty obvious thing that they need to stop when the bottle is full. But for a variety of reasons, it happens all the time where the bottle gets over full and you end up with product on the ground. So a fixed volume system is actually designed to overcome that, to prevent that. And the way we do that is by actually pre-measuring out a certain amount of liquid. So we've actually got a sample cylinder in our schematic, and you can see it here on the panel, that is permanently affixed to the panel. And we use that to pre-measure out a certain amount of liquid, and then we actually use our purge gas to transfer that into the bottle. So let's take a look and see how that works. So when we first walk up to our panel, in this case, we've got a 3-valve geared assembly. And this is our continuous flow version of this panel, which means we always have the flow from the inlet to the outlet. And that's what this third valve actually gives us, is the ability to do that. So when we first walk up, we've got that flow from the inlet to the outlet. We've got our purge gas, but it's shut off. It's not going anywhere. So we go to the flush position, and that switches these valves and allows us to now flow through that sample cylinder that's affixed to our panel. Again, this is not something we're going to take off and transport to the lab. This is something that's permanently part of that panel. So we're just filling it up and using that to pre-measure out a certain amount of liquid. Now, once that little fixed volume chamber or cylinder is full, we can go ahead and switch to the sample position. And we are using that purge gas now to push the liquid out of our cylinder and push it into our sample bottle. And if we just let it keep running, that purge gas will just keep flowing through the top of the bottle, sweeping all those lines clean. So now everything's nice and clean. Our sample is completely transferred to the bottle. We're ready to take that bottle off to the lab for analysis, and we know that next time we walk up to take a sample, all those lines are going to be nice and clean. We don't have to worry about old sample in the line contaminating it. Now, how might we customize this if somebody needed it? Well, we could add a number of different things. Let's suppose it was a hot sample. We need to add a sample cooler. So we've got a sample cooler. And maybe it's dirty. So we've got add a little particle filtration to the sample as well, as long as we're not filtering out the things that we're trying to measure. And of course, then, what do we do with the vapors? Maybe we need to manage those vapors, so we add like a treated vent. Maybe it's a charcoal filter or something like that to manage the vapors coming out of that bottle as we're purging through. So, these customizations, these are really easy for us to do. And the reason it's so easy is because we consider these GSM and GSL, these product lines, we don't really consider them to be product lines. We really consider them to be a design platform, a starting point for customization. As a matter of fact, we would say that maybe 10 or 20% of these things are sold as is with, straight out of the catalog without any modifications. The vast majority are modified in one way or another, whether it's putting things onto the front of the panel like you see here, or mounting this GSL into an enclosure, or this cylinder arrangement here. This is another way of dealing with overpressurization, is to have a sample cylinder a relief valve that goes into a secondary sample cylinder. So there's a lot of different things that we can do from a customization standpoint, and it's really nice in that our local Swagelok sales and service centers around the globe are enabled to do this. So we actually have a certification program that teaches our sales and service centers all about grab sampling. So they have expertise in grab sampling, the concepts of it, so they can take our standard offering and then apply those best practices, apply their expertise to develop whatever it is that you guys need from a customization standpoint, and to suit your particular application. So that's really nice. That's all the content we had. Expect an email to come out from PTQ Digital Refining with more information about grab sampling. And of course, feel free to visit Swagelok on swagelok.com. We've got a nice blog called Reference Point, where we've got a lot of great information on grab sampling and other applications. And of course, you can follow us on your social media of choice, be it LinkedIn, Facebook, Twitter, all of those. So by all means, take time out to visit Swagelok online and on social media. Be happy to have you. And at this point, I'm going to hand it back over to Ken, and we're going to accept some questions and let you guys go ask whatever you like.
All right. Well, this was a popular one, and boy, do we have questions lined up. So we're just going to fill up the rest of the hour and get as many as we can. You're going to rapid fire these, Matt. And then
all right.
We'll take whatever's left over and take those offline and get back to people. I think I'm going to switch our display as well. I'm just going to put us on camera since there are no more slides. If you need to go back and show anything, let me know and I'll put us back on your slide.
Okay, sounds good.
All right, starting. Is there a minimum pipe size for a sample probe?
Yeah, typically we would say that, anytime over 2 inches, you start to think about a probe. Anything over 4, you definitely want to have a probe. 2 to 4 is kind of a range where you might get away with it, but anything over 4 inches, you're definitely going to want to have a probe. Anything less than 2 inches, and the effects of along the wall of the pipe are much more muted, and the benefit of a probe is much less.
Okay. Question about pressurized systems. How do you keep a retractable probe safe, not become a projectile?
That's a great question. Yeah, if you loosen that gland fitting while it's under pressure, obviously the pressure is going to try to push that probe out of the system. Two different safety measures that you can put in place to manage that. One is a safety chain. So a safety chain allows you to more or less lock that probe in place. So even if somebody were to loosen that fitting, the chain would pull taut and prevent it from shooting out. And the second is actually a safety collar that gets welded to the end of the probe, and so to the tip of the probe. And so when you're withdrawing the probe, that safety collar actually catches on the gland fitting and prevents it from coming all the way out. So those are the two main safety measures. There are also devices that some sell that enable you to retract that probe while under pressure. But yeah, those are less common. I would say that the chain and the safety collar are pretty common. The safety collars on pretty much all of them. The chain less so, but still pretty common.
Okay. Question about ASME code requirements. And specifically, are there any that we need to deal with when we're talking about retractable quills design and safety?
Um, Not really. I mean, the design codes generally apply to these things, so B31.1, B31.3, but uh, there are no specific codes that I'm aware of that specifically apply to the design of probes or the implementation of probes. Um, y- you know, Most of that is through academia and the best practices, the theoretical best practices, and how they're applied. But I'm not. I there may be standards out there, but I have not seen them if they are.
Okay. Eric gave me, wow, a lot of questions about cylinder fill orientation, which you talked about a little bit, top to
Hmm.
bottom, bottom to top. Does it make a difference based on different types of samples, whether you're doing crude oil or benzene concentrate, gas
Yep.
versus liquid,
Yep.
dealing with bulk flow water, sediments, etc.?
Yeah. So in general, for a liquid, we're going to say fill from the bottom up. With that, you don't want to, you want that gas to be able to escape out the top, or at least the gas that we want to escape. Again, we may want to have some sort of a vapor space up at the top of the cylinder, but by and large, you want to be able to control that how much gas is left in there, and it's easiest to do that vertically. If you have the cylinder horizontally, then all that sediment and stuff like that you mentioned, that would actually collect in the cylinder. And that's not, you probably don't want that. You probably don't want that. Not that, and also you end up with the top half of the cylinder is full of gas because again, it can't escape anywhere. So from a horizontal and vertical perspective, you definitely want to go vertical. Again, a liquid we're typically filling from the bottom up. And a gas we're typically going to fill from the top down, and that allows any condensate to flush out the bottom of the cylinder. Now, with a gas, if you're filling from the from the bottom up, if you have any condensate in your line, that could get flushed into the cylinder, and then you can end up with a cylinder that has a pretty significant amount of condensate in the bottom of the cylinder itself, and that's probably not what you're after because again, that's not going to be representative. So, again, with the horizontal orientation with a gas, again, if you have condensate, you're going to end up with a lot of condensate collected in the cylinder as well. So vertically is what we would say, as opposed to horizontal, and then fill the liquids from the bottom up and the gases from the top down.
Great. Question asking, this is a bit open ended. What factors should we understand or consider? Excuse me. What factors should we understand or consider when converting from an open system to a closed sampling system?
Yeah, so open sampling versus closed sampling. Of course, the first thing to consider is, do we have some place in the process to send that sample back to? So do we have some place with a lower pressure that we can send it back to, and does that tap exist? So that's probably the very first consideration, or sample disposal. The next consideration is probably again that the you know the container type. Are we going to go bottle? Are we going to go cylinder? And do we need a lot of pressure in order to drive that through the system? So the viscosity of the sample is going to come into play because now we're transporting that sample twice as far. We got to go to the sampler and then back again. So do we have enough pressure drop? So those are probably the first things you think about. And, the thing that probably drove you to to considering a closed sampler in the first place is going to be toxicity of the sample, and then also potentially the waste disposal. Much easier to put it back into the process than have to deal with it otherwise. So those are some of the factors that I would consider when moving from a open system to a closed one.
Okay, great. Adam says, for quick connects, we face elastomer challenges for low temp hydrocarbon applications like ethane, butane, etc. I've heard Swagelok is looking at elastomer options, maybe low temp Calres. Are there suggestions or updates in regards to this type of service?
Yeah, we don't really have a ton ton of options at the really low temperatures. You got your Buna Cs, which can go pretty low. Your EPDM as well, but EPDM obviously, typically doesn't work really well for hydrocarbon service. So you're typically looking at your Bunas that can go relatively low, maybe maybe as far down as -50, -60 Fahrenheit type of a range. Below that, you're really kind of into the area where maybe you can get away with Teflon in some cases, but your Teflon is going to start to be fairly stiff at that temperature as well. So yeah, you start to run out of options at those low temperatures, unfortunately.
Okay. For oil sampling, is there
Mhm.
any requirement from APMPMS 8 in order to generate a pressure drop to make a circulation of the sample to the recipient to be representative?
To be honest, I'm not familiar with that standard, so I couldn't say what that standard says in particular. Um, I I would say that it's definitely a best practice, because again, from the length of that sample line from the tap to the sample panel is going to be full of old fluid. So you really want to be able to flush that out before you take your sample into the sample container. So from a representative standpoint, you definitely want to have that returned to the process or to some other disposal area so that you can actually flush through the panel, get a nice fresh sample, and then make sure that your sample is representative. Now, to that particular standard, again, I'm not familiar with it, so I can't say one way or another, if that requires it or not.
All right. Well, we are getting close to the end of the hour. One of the things we've learned from past webinars, people have told us they need those extra couple of minutes to get their papers in order for the next meeting on the hour. So I'm going to shut us down. We still have a few questions in the log here. We're going to take those offline. Definitely, we'll get back to people. Matt, thank you so much for bringing us the information today.
Sure. Thank you for having me, and thanks for listening, everybody.
On behalf of Swagelok, that concludes our webinar. Thank you and enjoy the rest of your day.